Okay. Now remember what we were calculating. This is 0. This is what I'm trying to calculate. The first term was already 0. I'm looking at the second term, and I had calculated this one. And diagrammatically, I had shown that V and I is actually given by twice K1, K2, K1 prime, K2 prime, plus twice K1, K2,
May I ask a question?
K1 prime, K2 prime. Yes.
So, let's say we start with an initial state that K1 and K2 is equal to each other. Now, with diagrams, we are just writing that as if there are two paths and there are two different places of creation in the intermediate state. But when K1 and K2 equal to each other, there should be a 4 of the same thing.
Okay.
But by saying that K1 and K2 are equal to each other, we are not actually saying that K1 and K2 are identical particles. Maybe they are not. So how should we interpret K?
Now,
Is that I don't know, a valid question?
well, I'm already saying that these are identical particles implicitly.
By saying that
I am imposing commutation relationship, so I'm already symmetrizing everything. So basically, this is a symmetric contribution. But let's just leave it for the time being.
We had also said that they were created by the same fields. So they were created by same fields.
Yeah. They are identical particles, they are same fields. Furthermore, they are bosons. I'm talking about scalar fields. They are bosons because I impose commutation relationships. Now, let's look at VFN. Well, it's not I will not be doing the same computation over again. You see, all these diagrams, what they have in common is they have momentum conservation at every step. Further, at every vertex. And, well, for each diagram contributes a factor lambda. You see, if you look at what I had calculated over here, each diagram contributes a lambda with momentum conserving Dirac deltas. So in fact, I can straight away write what VFN VNI. I can straight away write these factors. So I have this one where this emits the second kind of particle. The other one should absorb the same kind of particle. I have K1 and K2. And here, let's say at this state, they are K1 prime and K2 prime. And at this step, they are P1 and P2. Plus, I have two of them. Plus, I have from the other diagram, this is K1, this is K2, this is K1 prime, this is K2 prime, this is P1, this is P2. Now that additional factor of 2, you see, I always connected K1 prime with P1, but K1 prime might also connect to P2. And they will basically be the same diagrams. Well, if K1 prime is, well, they will be the same diagrams. They will have the same contribution, so that's why I have the 2 there. So what is the corresponding term? Let's say this is my intermediate state. I have this VFN will be, there is a sum over all intermediate states. You see now my intermediate states, the number of particles in my intermediate states, at least in these contributions, are fixed. The only thing that they can have differently is k1 prime and k2 prime. So this is an integral over d cubed k1 prime, d cubed k2 prime divided by 2 pi cubed. And then I have, you see, at each one of these vertices, there will be a factor of lambda. And then I have energy conserving Dirac deltas, momentum conserving, 2 pi cubed. Let's say the first diagram will be Dirac delta P1 minus K1 prime 2 times 2 pi cubed Dirac delta K2 minus, let me call this K5, Dirac delta K2 minus K2 prime minus K5. This is the energy momentum conservation here. Then I have Dirac delta K1 prime plus K5 minus P2, and sorry, I have another d cubed K5, and I have Dirac delta K1 minus K1 prime, Dirac delta K2 prime minus P2, 2 pi cubed, 2 pi cubed. You see, there is one V matrix element over here. I have energy conservation. So there is one V insertion here. Right over here. I have momentum conservation at the lower vertex. At the upper vertex, K1 prime and K1 and K1 prime should be equal. This is K1. That is this other Dirac delta. Look at this expression over here. At each vertex insertions, I have 2 Dirac deltas. So when I multiply 2 V's, I get 4 Dirac deltas. This is the contribution from the first diagram. And from the second diagram, I have, let's see, there's a vertex here where I have 2 pi cubed Dirac delta K1 minus K1 prime minus K5. This is K5. And Dirac delta K2 minus K2 prime. There is another vertex matrix V potential matrix element over here, which will give me a Dirac delta K5 plus K2 prime minus P2, Dirac delta K1 prime minus P1. Well, I have 4 factors of 2 pi cubes. And when I integrate, I can use those Dirac deltas to integrate over K1, K2, and K5. And I will, and there is also 1 over E minus E, and let me call that 0. Here, 1 over E minus E and 1. So what I will get, 4 lambda squared, 2 pi cubed. I will have Dirac delta k1 minus k plus k2 minus p1 minus p2, the overall momentum conservation. 1 over E minus E, and, well, let me call them 1 and 2.
It's for the type of the particle.
No.
First order?
E and 1. So you see, here I have an intermediate state, which has energy E and 1. Here I have another intermediate state with an energy E and 2. Both are 3-particle states. Okay. So what do I get? I get an overall energy momentum conservation. No, not energy conservation, but overall momentum conservation. Then I have these 2 factors. Now let me look at what En1 is. En1 is equal to, well, I have momentum k1 prime, k5, and k2. This is for the first kind of particle, omega k2 prime. Well, k1 prime is actually k1 because of the Dirac deltas. So that is omega k1. Omega k5. And then I have here omega p2. That is the energy of this intermediate state. I have 3 particles having momentum k1, p2, and k5. En2. What is En2? En2 will be, I have here, at the upper line, I have a particle with momentum k1 prime, which is p1. So this is omega p1. Then I have a particle with momentum k5. And then I have another particle with momentum k2 prime, which is k2. Yes.
P1 and P2 are the solid external legs of this diagram, right? They are not in the inside, so why we have as an energy? It should be K1, K5, and K2, and K1, K5, and K2.
No, you see, it will be omega k1 prime. If you look at the first term, for example, this one,
yes.
Here I have omega k1 prime.
Yes, K1 prime.
So there I should have omega k1 prime. But look at the Dirac deltas. This Dirac delta. K1 prime is equal to K1.
Okay.
So when I integrate over K1 prime, omega K1 prime becomes omega K1 due to
and K2 prime becomes P2. That's why it's below.
Yep. So you see, okay, some of you were already asking about virtual particles. Each particle has a given energy. I have energy violation. Energy of a particle is always given by square root of p squared plus m squared, if that is our H0, let's say. But we stick with that. So each of these omegas is actually square root of p squared plus m squared, m being the mass of the corresponding particle. And By the way, they are all positive. There are no negative energies. Omega is how we defined it to be. Omega is something we define to be positive. We put the possible negative signs in all other places. Everything is so-called on shell. They satisfy this condition. Now let's try to simplify this a bit. This expression, you see, we have, I will be looking at this factor. What is that factor? And, well, let me just write it. 1 over E minus E and 1 plus minus 1 over E minus E and 2. Well, let me first combine, let me write it first out explicitly. E minus omega K1 minus omega P2 minus omega K5 minus 1 over E minus omega P1 minus omega K5 minus omega K2. Now minus or plus? That's plus. You see, in this, okay, if I go back, in this expression, now I already evaluated that expression, by the way. That expression is given by this term, this whole thing. And the only thing that I need to somehow simplify is that sum over 1 over E minus E ends. And they are these expressions. I will use one more thing. E is equal to omega K1 plus omega K2, which will be equal to omega P1 plus omega P2. I will use overall energy conservation. Not at the intermediate states, but in the overall, the energy will be conserved. Well, let's see. This is P1. So let's choose to write everything in terms of omega K2 and omega P2. So what does that tell me? 1 over omega P2 is something I like. E minus omega K1 will be omega K2 minus omega P2 minus omega K5 plus 1 over E minus P1 will be omega P2. Now this is omega K2 minus omega K2 minus omega K5. Which will be 1 over let me say omega K2 minus omega P2 minus omega K5 plus 1 over minus omega K2 minus omega P2 minus omega K5. So when I sum those two terms, I will end up having minus twice omega K5 divided by Now let me just take that minus also out. Omega k5 squared minus omega k1 minus omega k2 squared. K2 P2, sorry. Now, everything is fine up to this point. Well, let me go back to my diagrams. This is the diagram I'm looking for. This is omega K2. This is K2, P2, K1, P1. I'm adding the other one also. I know that there is momentum conservation over there. So this K5 is equal to K2 minus P2. No, this is P1. So K5 as a vector is K2 minus P2. Let me define K5 0 as K2 0 minus P2 0. I'm just making a definition. So my factor is now twice K5 0 divided by K5, twice omega K5 divided by omega K5 squared minus and this is omega K5 squared. Okay. Remember the definition of omega K5. This is K5 squared plus M2 squared. Yes. So omega K5 squared is K5 vector squared plus M2 squared. Which is twice omega K5 divided by M2 squared minus K5 0 squared minus K5 vector squared, or twice omega K5 divided by M2 squared minus K5 4 vector squared. Okay. Okay, so what have we done? I essentially have these two diagrams. As we have seen before. When I sum these two diagrams, now these two diagrams basically have exactly the same contribution. You see, those two diagrams have exactly the same contribution. And this will always be the case. Whatever system you have, those two diagrams will have exactly the same factor over here. Multiply by these two terms. Each one of those terms in the sum correspond to one of the diagrams. When I sum those two diagrams, I will have what we will usually draw like this. One is not before the other one. This is what is called the Feynman propagator. It is basically the sum of those two propagators, this one and this one. Remember, 1 over En minus Ei is what we call the propagators. There are two terms with different propagators there, but except then the propagators themselves, everything else was the same, so we can just sum those two propagators. When we sum those propagators, we obtain what is called the Feynman propagator, and the Feynman propagator for this particle turns out to be this factor, 1 over m2 squared minus k5 squared. K5 squared is the 4 vectors squared. Zero component, I mean, we only had the conservation of the 3 momentum. But now we define a 4 momentum. We assign a 4 momentum. The particle doesn't have this 4 momentum, but we assign a 4 momentum to this particle in the intermediate state and impose 4 momentum conservation at each vertex. You see, this is the 3 momentum conservation. This is the 4th component conservation. We impose the 4 momentum conservation at each vertex. And then if we assign this 4 momentum to my particle, the corresponding propagator, the corresponding Feynman propagator is just 1 over the mass squared minus the 4 momentum squared. Now, keep in mind that for, let's say, P20 and P23 momentum, if you look at this 4 vector, take its squared, this is M1 squared. 4 momentum squared of a particle is equal to its mass squared. But when I assign this 4 momentum to my intermediate particle, its momentum, 4 momentum squared, will not be equal to its mass squared. In fact, if it is equal to mass squared, you will get divergences. So this is sometimes called, that intermediate particle is so-called off-shell. So this is just the terminology we will be using. We can have on-shell particles. Those are particles for which their 4 momentum squared is equal to their mass squared. This is the on-shell. Off-shell particles are particles whose 4 momentum is not 4 momentum squared is not equal to their mass squared. And the zero component of these particles, K50, if you in general, if you have a 4 momentum of a particle, the zeroth component is its energy. But here we see that K50 is not equal to omega K5. So the zeroth component of these particles is not really their energy. Now, off-shell particles, or particles whose zeroth component is not equal to their energy, we also sometimes call them virtual particles.
Should we write minus m squared? Minus mu equals minus m squared?
No. No. P squared is equal to m squared if you are not one of those weird gravity guys.
Just something that I just think about, but I won't ask. What we mean by on-shell is basically if the equations of motions are satisfied, right?
Yeah, you see.
What we mean by off-shell is
No, you see.
the equations of motions are not necessarily satisfied.
Let's look at my states. What were my states? We have K1, K2. This was one of my states. I said that E of this state is omega K1 plus omega K2. And if you want the momentum of this state is K1 plus K2. And EI squared minus PI squared is not equal to twice m1 squared, by the way. But if I look at each one of those particles separately, omega k1 squared minus k1 squared is m1 squared. Omega k2 squared minus k2 squared is equal to m2 squared. My intermediate particle is this one, intermediate state. Let me just write k1, k2. I mean, one of them will be p, but or one of possible intermediate states was this one. The energy of this state is omega k1 plus omega p2 plus omega k5. The momentum of this state is k1 plus k2 plus k5. Each one of these particles, for each one of them, I have omega k1 squared minus k1 squared is equal to m1 squared. Omega p2 squared minus p2 squared is equal to m1 squared. Omega k5 squared minus k5 squared is m2 squared. So which energy non-conservation, which equation of motion non-conservation are you talking about?
Is it m2 squared?
Yes, m2 squared.
Okay, then if there's no problem with omega being equal to k, because m2 would be 0 then.
Yeah.
But that would give divergence to the probability.
Omega k5 is not equal to k5 0. That is what saves me from the divergence.
Yeah, but this basically indicates that
K5 squared is not equal to m2 squared.
So if I have a particle, let's say I have a Lagrangian, I solve the equations of motion, in which I find the p square equals to m2.
Okay.
In this case, it does not satisfy.
What is your p? 5 k1.
That's my state.
That's my state. What is my p? If I would like to use the equation of motion and all of that, I would say that my p for this state is omega k5 and k5. And it satisfies my equation of motion. But then I invent another vector, another 4 vector, where the 0 component is not omega k5.
That doesn't satisfy the equation of motion.
That doesn't satisfy the on-shell condition.
Which is the equation of motion in momentum space.
Which equation are you talking about? Let me ask.
If I change omega k5 to omega k5 0, which is not equal to omega k5, then the equation of motion in the momentum space is not satisfied.
For the virtual particle.
For the virtual particle.
Well, I mean, I can put there 5 GeV and it will not be satisfied, but what does it tell me? Nothing.
No, what I was trying to say is this. When we prove the conservation theorems, we basically assume that the equations of motions are satisfied.
At this derivation, at every step, every particle satisfies the equation of motion,
Even the virtual particle.
even the virtual one. You see, here I use this equation to derive this propagator. Omega k5 squared is equal to k5 squared plus m2 squared tells me that the fifth particle, this phi k5 particle, satisfies the equation of motion. Omega being its energy, not k5 0. But of course, the terminology that we in general use is This K5 particle has the zero component K5 zero, which we derive using energy momentum conservation at each, for momentum conservation at each vertex. And if you identify that with the energy of, with the zero component of the particle, then of course you are changing everything, and hence those for momentum doesn't satisfy the equation of motion in momentum space, because the equation of motion in momentum space is this one: p squared is equal to m squared. But you see, meaning we in general invented this K50. I just made such a definition.
Then can I ask something?
And by the way, those four things form a four vector in the real sense of it, because that K50 is the difference of two four vectors. So that difference is actually a four vector. I can play with it. I can try to assign significance to that, saying that, oh, that is the zero component of that particle, and if that is the zero component of the momentum, and hence it doesn't satisfy my equation of motion. That is the terminology we use. But there is nothing, all the particles are satisfying my equation of motion from the beginning. That is how I construct my states.
But within that terminology, can we state the following sentence? In the intermediate states of this interaction, the energy is not conserved because there's virtual particle that is off shell. And since it is off shell, the conservation theorems do not work because it requires equations of motion to be satisfied.
You see, what do you mean by conservation? If you want to use this terminology of for momentum, the zero component is energy. You are inventing this for momentum to make sure that you have some energy momentum conservation. You see, this is, I am imposing, if you identify K50 with the energy of the particle, let's say, that's one way of looking at this. The particle has energy K50 because I'm imposing energy momentum conservation at each vertex. But then this particle no longer is on shell, and hence it doesn't satisfy the equation of motion anymore. Or I can say that, well, forget about that for zero component of that four vector. I can always keep working with omega K5. All the particles have energies equal to square root of their linear momentum plus mass squared, but then I don't have energy conservation in the virtual state.
My confusion is that maybe, I don't know what, so I expected that in the end, if we find something that is called a Feynman propagator, then the end product that we find, that the things that we find, that it should be independent of the virtual particle and should be Lorentz invariant. But
You see.
I guess this is not right. So this is why I imagine that it should be only depending on the external legs of the diagram, because they are the in and out. But we have mass dependence, so it's not Lorentz invariant, I guess.
No. This factor is Lorentz invariant.
The whole factor.
Hold on. 1 over this is Lorentz invariant. K5 that I defined, since it's the difference of two four vectors, is a four vector, and hence its squared is Lorentz invariant.
4K5.
Yeah, this is 4K5 squared. M2 is just a mass, it's just a parameter. It is Lorentz invariant. So this is Lorentz invariant. This 2 omega K5 is not Lorentz invariant, but I mean, those are just the normalization things. I would have expected it to cancel with 1 over 2 omega K5 somewhere from the K5 integral or somewhere else. So I wouldn't bother about that 2 omega k5 at the moment. But the remaining part is Lorentz invariant. Also keep in mind that we have been working with energy all the time. Although we have been working with the energy all the time, which is not Lorentz invariant, the final result is Lorentz invariant. So we have a Hamiltonian system. We are looking at the system from a Hamiltonian perspective. Although we know that the system has to have Lorentz invariance, that's how we construct the Hamiltonian. But at the intermediate stage, since we have energy explicitly appears, it doesn't look Lorentz invariant, but the final result will be Lorentz invariant. And so that's also another reason why we prefer the Lagrangian formalism. At the end, we should get Lorentz invariant expressions for quantities that are Lorentz invariant at least. Not everything will be Lorentz invariant, but Lagrangian formalism will make it explicit. Even in the intermediate steps, everything will be Lorentz invariant.
One last question. By saying that the virtual particle itself is off shell, we are also stating that we cannot write a corresponding operator that will give us a real eigenvalue, for example, so that it's an observable. So virtual particle itself is not an observable, or not. I don't know what it says.
What is a virtual particle?
In that sense, for this diagram at least, it's a particle that we create to conserve the momentum.
No, the system tells me that I should have an intermediate particle which appears in the intermediate states and disappears at the end.
Okay.
And for those kind of particles which doesn't appear at the beginning, initial state, which doesn't appear at the end, which only appears at intermediate states, I can sum these two contributions explicitly and obtain this propagator.
That counts
But-
both of the graphs.
Yeah, but by definition, it shouldn't appear at the initial state, it shouldn't appear at the final state. So that is what we call a virtual particle. It doesn't come to my detector. I'm not creating it, and it doesn't arrive in my detector. If it arrives in my detector, then it won't be a virtual particle. By definition of the virtual particle, it shouldn't appear neither in the initial state nor in the final state.
But we can still somehow deduce their existence due to the cloud chamber experiments.
No, the particles that you see are not virtual particles in cloud.
I'm talking about what we don't see. For example, we have a cloud chamber experiment in that two particles collide in position X. Then some time passes and two particles are created in opposite directions in the point X prime.
Okay.
As if something we don't see created in the X position goes to the X prime and annihilates into two visible particles.
Okay. You don't see it?
We
Still.
don't see it, but as if it looks as if something was there.
So, you see, these diagrams also look as if something was there. We see the effect. The particles change their momentum. But we don't see them directly. So we look at all the process that we see, we look at the initial particles that we send, we look at the final particles that we observe, and anything that might have been created during this process is what we call a virtual particle. Are they really created?
Yes, it should.
Why?
Because
Can we say anything about it?
I guess we can.
Yeah.
At least we can, I don't know, circle around and say that for P2, to have that P2 momentum, we need to have some kind of a particle in between with this energy and this momentum, so that we have the P2 in the end. We are seeing the P2 in the end, so there should be that kind of a creation and annihilation in between, right? We are circled around it, but in the end, it should be the same understanding, right? No?
You see, when you see this sum, you won't go ahead and invent new particles, right? When you see such a mathematical expression. But then, we just draw pictures showing exactly the same term. This and this are the same thing. If on the left mathematical equation you don't see any new particles, why see it on the right? Yes, this is just one means that, one interpretation that we tend to visualize it. But, I mean, giving it more meaning than that might be misleading.
So can you say anything about what is happening between those two particles? I mean, they are surely interacting because their momentum
Right.
changes.
I can give you one picture. That, oh, I have these other particles being created, they are exchanging particles, and hence they are exchanging momentum. That is one picture that I can come up with from this computation. But I'm sure there are other pictures. I can solve all my equations numerically, and there won't be any particles in any of my equations, for example. It will be a black box. Something goes in, something goes out. Or I have this field picture, where I have these sheets, they are vibrating, and their vibrations change in time. Again, no particle, a picture without any particles.
I can also add additional virtual particles, right? If I change my Lagrangian or my Hamiltonian, such that there's phi 3 field, let's say,
Mm-hmm.
which can also create an annihilated within this picture. I can also explain this same coefficient with or without this additional field.
Okay, so
it's the Arkham razor, sir.
hmm?
It's the Arkham razor. The explanation that I have with the minimum ingredient is this.
Okay.
And this picture doesn't yield the fact that there's a particle that is created and annihilated within that region. Because also I can explain this with many other particles included.
No,
Why?
because you see, if you think, especially in terms of models, you are writing models which can have many particles, and then you try to measure them. You see, if you have two particles, most likely in some processes you will see different contributions, so you can eliminate them. But, I mean, at least if you want to use that argument, I would rather go for a hypothetical particle which doesn't interact with anything. Then I
was
would-
actually saying Russell's ideal teapot ideal. There's a teapot in the universe somewhere that
Okay.
explains everything. Something like that. In this process, there's a teapot created and annihilated without even interacting with any of this. This can also include it to this picture.
You argue in this sense, I guess, right? If I understand correctly. So we have a momentum K5, a virtual particle. We might have n particles virtually created in the total momentum K5 addition. So they will be the same picture or not?
No, if you create more than one particle at the intermediate state, it will give different contributions. So what he is saying is I can have phi 2 field propagating this force or phi 3 field propagating this force. but one of them is enough, so I imagine the other ones don't exist. That's what I understood from Arda's argument. But you see, I can also have these fields vibrating, picture. There's one field vibrating. It causes the other field to start vibrating temporarily, and then that second field vibration is again that vibration energy is transferred back to the first field vibrations, so there's no particle there. That's another picture. But at the end of the day, these are just pictures that simplify our life. So I tend to, whenever I'm studying such processes, I say, okay, there is this particle created, it propagates to the other particle, and there's a momentum exchange. Okay, that's the picture I have. But it doesn't mean that it actually happens, or that this is the only way of picturing the process, or it doesn't also mean that this is the only way to calculate that process. For example, you have models of bosons which have fermionic excitations, which cannot be treated as just a bunch of particles. So this particle interpretation, there are some limits to that. It's just a good advice to keep that in mind. This is just a picture we are having. Okay, let's finish today.